All right. Good morning, good afternoon, depending on when you're watching this. Today, we're going to be covering our final section of this course. So this is the final section of Chapter 3, 314, and it is going to cover scientific notation. So last time, we only covered 313. It's a pretty hefty section. With a decent amount of examples. So that was on perimeter area and volume of everything except pretty much circles, because we had covered circles back in chapter 2 when we did multiplication of decimals. And I even mentioned back then that the section was a little out of place. The reason we put it there is because it involved multiplying decimals because of the pi with its approximation of 3.14, but that it really arguably fits better in this section 313, not this section we're looking at, glass classes, section 313. But again, there's nothing wrong with just taking a formula and putting it in another section. Excuse me. So for our final section, scientific notation. And I will admit, this is not something that you're going to use a ton of. It's not going to be used with heavy frequency in quantitative reasoning, but it is used. It's not something that's going to get used with heavy frequency in pre-calculus, but it is going to get used. It's not something that gets used super frequent in calculus, but it gets used actually a little more frequently, quite honestly. The higher up you go, the more often this stuff starts to get used. So what is scientific notation? Why do we have it? And how do we use it? All right, scientific notation is just a different way of representing numbers. So let me just give myself some space. So for example, the number 567, this would be in standard notation. Oops, I hit my button. But if you wanted to see this in scientific notation, its equivalent is 5.67, then a times 10, and then it would have an exponent that's a 2. Now, here's the reasoning for this. This times 10 to the 2, that's really 100. 10 squared is 100. So this is saying that it's 5.67 times 100, which takes the decimal and moves it right twice. We talked about multiplying by powers of 10 or even decimal powers of 10, tenths, hundredths, thousandths, etc. Just moves the decimal place left or right, the number of zeros or decimal places, which is in fact 567. This is just me showing that this number is accurate. So 10 squared is just 100. We know how to handle exponents. So scientific notation is just a different representation of your standard number. But what's going on here? Well, we have this times 10 and an exponent. This times 10 is always here. You always have a times 10, and you can see that down here in this notation. This number up front, I don't know why I just switched to blue, but whatever. Apparently now that I started using different colors, it just wants to switch them on its own. This number, this 5.67, has to be between 1 and 10. It has to be a single digit in the wholes. In other words, this 5, it can't have a 15. It can't be 56. It can't be 0.5. It has to have one single non-zero number in front of the decimal, which means it has to be between 1 and 10. Now, it can be 1, but it can't be 10 because that would give it its extra digit. So there's only a number in the ones place when we're in scientific notation. And then you can have however many numbers after that. So basically, what our goal is to do in standard notation to go to scientific notation is to take the decimal place in the number, which if you don't see it originally, it's at the end, and your goal, oops, I always forget I can't write on the margin. I don't always forget, I'm getting used to it, but I sometimes forget. The goal is to get that decimal there. So you need to take this decimal and move it left 1, 2 times. Because we move the decimal 2 times, that is why the exponent is a 2. Now, the only thing is, sometimes these exponents are positive, sometimes they're negative, and it depends on the direction that you move your decimal. The sign of the exponent depends, it's a terrible looking P, on the direction the decimal moves. So, going from standard to scientific, if the decimal needs to move left, it is a positive exponent. If the decimal needs to move right, it's a negative exponent. So if the decimal needs to move left, it's a positive exponent. If it needs to move right, it's a negative exponent. That's the rule. Now I'm going to give you kind of a helpful way of remembering this, because we're going to practice a couple standard to scientifics, but then we're going to introduce how to go from scientific to standard, which is completely opposite about everything. So now it's if the decimal moves left, or sorry, now it's if it was a negative exponent, the decimal moves left, positive, you move it right. Everything's flip-flopped when you change directions of what you're trying to do. So what some students have a problem doing is getting the directions right for each set. They might have it, oh, left is positive, right's negative, and they'll do that no matter what, but it's only true for one of the processes. So I'm going to give you a way to remember this. I find it very helpful. I find a lot of students find it helpful if they actually try and remember it, which you should. So then we will go from there. So let's practice this. Writing numbers in scientific notation. So 1, 2, and 3. So we have 38,000. So our goal with this 38,000, so I'll rewrite it to the side. Actually like it in blue for this. We need that number to have a decimal. It didn't have one, so we put it at the end. We don't get to decide where it goes. Remember, we just have to put it at the end. It's really interesting. This thing beeps at me sometimes, and I have no idea why, because I don't even have any students in here. Okay, so we're supposed to move this decimal so that there's only one number in front of it. So we only want the 3 in front of it, so this decimal's got to go left. 1, 2, 3, 4 times. So that was left 4 times. So the 4 is our exponent. So we know we're going to have a times 10, and there's going to be a 4, but it's a question of whether it's positive or negative. If we move the decimal left, it's supposed to be a positive exponent. So this is a positive 4. So this is 10 to the 4th, which is what, 10,000. So this represents 10,000, and in front of it, we just write this number as we moved the decimal place, or after we moved the decimal place. So we put it between the 3 and the 8. So this is 3.8. Now you might say, Mr. Beckner, what happened to the zeros? Why didn't you write 3.8000 times 10 to the 4th? Because we don't need these zeros. These are trailing zeros. They don't affect the problem. With those zeros there, without those zeros there, it's the same thing. So we don't need trailing zeros. Also, if there were any zeros in front of this 3, they'd be called leading zeros, and we would not need them. Spoilers for one of the next problems, maybe both of them. But there's the answer in scientific notation. If you don't trust this, you can rewrite the 10 to the 4th as 10,000, multiply it by 3.8, and you'll get 38,000. For number 2, we write our 0.053, and our goal is to have the decimal behind the first non-zero number, which is the 5. So the decimal needs to end up between the 5 and the 3, so we're going to have to move it right 1, 2 times. So that was right 2 times. Now again, these zeros in front, these would be leading zeros. So we don't need to write them. I don't need to write 005.3 because these zeros are unnecessary. I just need to write 5.3. Now, I can't promise that Connect will give you the right answer if you write the zeros in front of it. A lot of programs won't because they're saying you're not writing the number in simplest forms. Handwritten test, it's something I could be lax with, but we're not getting that, right? This course never gets that. We need you to understand how simple the number is supposed to look. So then we have our times 10, and you can use a dot instead of an X as well. That doesn't matter. And then the exponent, since we moved it twice, has to be a 2, but, excuse me, but we moved it right this time, which means the exponent's supposed to be negative. So that's a -2 here. Now, we don't really address what negative exponents mean in this course. I'll say it in passing. It means that the decimal place moves left. So this 10 to the -2 is like having a decimal move left twice. So it's a decimal value number. It's not going to be 100. The decimal goes the other way. So 10 to the 1 would be 10. 10 to the 0 would be 1. 10 to the -1 would be 0.1. 10 to the -2 would be 0.01. I think I said 0.2, didn't I? 0.1 and then 0.01. I don't know. Maybe I did, maybe I didn't. So this number right here is really 0.01. That's what negative exponents mean. You move it left instead of right. But again, that is above our pay grade. That's for a later course. So if you took 5.3 times 0.01, you would get 0.053 if you actually did your decimal math. All right, number 3. So we're going to write our number, which is originally the 0.00007. 1, 2, 3, 4 of them. Good. The decimal needs to go behind the first non-zero number, which is the 7. So we're going to have to move this right. 1, 2, 3, 4, 5 times. Now, right means negative. You have to have that memorized. So again, we don't need all these zeros in front of the 7. We just need the 7. Now, if you write 7 point and then times, that's accurate, but really you don't need the decimal because it's a whole number. So you can just write 7 times our 10. The exponent should be a 5, but because we moved it right, it's a negative. Watching me do it is not going to help you. You have to practice. How many times have we said that over the semester? I know, but it's the same thing, and I'm going to keep saying that to you in your next math class you have me with if you have me. Repetition is key. Let's try a couple more with some applications. So I asked earlier, at the beginning of the course, I said, what is scientific notation? Why do we use it, and how do we use it? We went over what scientific notation was, we went over how to use it, but I didn't go over why to use it. This is why we use it. Problem number 4, specifically. Really, 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 really big numbers, or really, 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 really small numbers, which we don't have an example in this class, but 0.000000000000297 would be a very small number. It's very tedious to have to write all those zeros if you have bad eyes like some of us. I'm pointing at myself. You might lose track of the count of zeros and mess something up. So scientific notation is going to take this number that's like 3285 with a bunch of zeros after, or 0.0000000, and then whatever 3 digits I said, 269, I don't know. And it's going to make that look a lot smaller. So I am not going to rewrite this number. I'm just going to put it in its place. So let's see. The decimal that is not originally seen is all the way over here. And it needs to go between the 3 and the 2. So there's only one non-zero number in front of the decimal. It's going to have to go left a lot. 1, 2, 3, 4, 5, 6. Every comma is 3. 7, 8, 9, 10, 11, 12, 13, 14, 15. Sorry if those bumps aren't perfect in a couple places. I'm doing my best with this tech. And I lost my count because I'm talking 3, 6, 9, 12, 15. Okay. 16, 17, 18, 19, 20, 21. We're getting there. 22, 23. So it moves 23 times to the left. Moving it left means it's supposed to be a positive exponent. Again, do 20 of these and you'll get used to it. If there aren't enough in the homework, do them again. Go to the internet, find more. Go to whatever resource you have to and connect to the internet to practice this more. So all these zeros at the end, they're trailing zeros. We don't need them, but I do need the 3, 2, 8, and the 5. So 3.285. That's all I'm going to write for the value itself. But then to show you how many times the decimal would move to go back the other way, we write times 10 to the exponent's of 23, and it should be positive because we moved it left. Remember, if you don't trust this, at least you know how to work out the positive exponent case. So what you can do is, okay, 10 to the 23, that's a really big number, which moves this decimal right 23 times, and boom, it gets the same thing. So if you thought number 2 was a positive exponent, that would make this 100. 5.3 times 100 would be 530, which is not the original answer, so that says, nope, the exponent should be negative. If you thought number 3 was supposed to be a positive exponent, then you'd multiply by, 100,000, and that would give us 700,000, which is not the original value. There is a way to check these, but only against positive exponents. So if you have a negative exponent, what you could say is, all right, what if it was a positive exponent? What would this turn into? And see if your answer is right or wrong. That's my suggestion. A dime has a diameter of 0.705 inches. So our goal, I'll write this one again so it's less crazy, is to get the decimal behind the first non-zero number, which is the 7. So it's going to have to go right, and not a lot, just once. Just write one time. So we'll write 7 point. Now you might say, oh, we don't need zeros. Let's just write 7.5. No, that's wrong. You don't need to write leading zeros. You don't need to write trailing zeros. So trailing zeros were the zeros from number 1. Leading zeros were the zeros from number 2 and 3. This 0 is sandwiched between two what we call significant figures. You have to write that. Otherwise, you're changing the value. Then we have our times 10. We moved it once to the exponents of 1. Now you might think, we don't write the 1 if it's positive. So I'll go back and skip writing the 1 if that's the case. But we moved it right, which means it's supposed to be negative. If you don't trust this, like I said, maybe you thought it was 7.05 times 10 to the first. Well, that's 7.05 times 10, which is 70.5, and that is not the original answer. So we are good. It is supposed to be negative. As I said, the way you can check these is just try it with a positive exponent and see if you get the right answer or not. If you do, if you had it positive originally, you're good. If you had it negative originally and it was wrong, then go back and make it positive. Don't just, oh, okay, I got the answer, let's move on. Oh, I got the answer, let's move on. Oh, I got the answer, let's move on. Take your time. So now let's try going the other way. Excuse me. And let's go to write numbers in standard form. Oops. Why is it taking that? I'm below it. That's wacky. So to go from scientific to standard, so now we're going the opposite way. The exponent tells how many times to move the decimal. And in what direction. A positive exponent says that you will move it to the right. Now I'm going to pause right there. If you see a positive exponent, you have to move it right. Let's go back to what we had before. We said moving it left, if the decimal needed to move left before, it's a positive exponent. Now it's right and positive. What gives? Because we were going the opposite direction down the street. So everything is flip-flopped. So now if you see a positive exponent, to unravel it, you have to move it right. If you see a negative exponent, you have to move it left. This is what I was mentioning previously that messes up so many students. They just start flipping coins in their heads because they don't want to practice this 10, 20, 40, 50 times. They want to do 2 of them and call it a day. That's not how your brain works. If you want to get stronger, you don't lift a weight twice and, oh, yep, all right, I got 10 extra pounds of bicep. You have to take time. You have to practice, practice, practice. You have to put energy into this. You get out what you put in. So I mentioned I have a nice little helpful way of getting this straight no matter which direction you're going. And it has to do with big and large numbers. So big numbers, and I say a big number is something 10 or larger, have positive exponents in scientific notation. Small numbers, which are less than 1, have negative exponents in scientific notation. I'm going to take this. I'm going to make it bigger for emphasis. I'm then going to take my highlighter and I'm going to highlight this whole thing. Because this right here is how I get every single scientific notation conversion problem right. I never memorized. Okay, that might be a lie. I don't want to say that. The way I do things now, at least, I don't have it in my head memorized that, I mean, I do, it's ingrained in me, but when I'm doing them, I don't say, all right, if I see a positive exponent, this is the direction I move in. I do it based on this. So if I'm supposed to go from standard to scientific notation, if I have a big number, I know that I'll make it a positive exponent. If I'm starting in a standard number and it's a small number, if it's less than 1, I know I'm going to make a negative exponent. Or if I flip the script, if I start with scientific and I got to go to standard, if I see a positive exponent, I should be making a big number, something that's 10 or larger. And if I see a negative exponent, I should be making a small number, something that's less than 1, like 0.1 or 0.01 or 0.001. I'm telling you, this right here is the key to success for this. Yes, you can memorize the movements in each direction and all that opposite jazz if you want to. Plenty of people do. But I know plenty of people that said this has saved them course after course after course. I taught this to a student in developmental math. Then later I saw them in calculus and they still remember this. So let's try that out. So for 6 through 9, we're going to write numbers in standard form, and we're going to use this little self-check to make sure it's right. I may even do one of these wrong at first, hint, wink, nudge. I may use red to signify it as wrong. So I got my red marker out, hint, wink, nudge. So this 5.12 times 10 to the 4th, we need to make this look like 512 with some zeros after it. Or it might be like 0.000512, something like that. We don't know. Then the number of zeros will depend on the exponent. So what you need to do is write the number in front of the times part, just the 512. Just write that, 512. Write it with its decimal, of course. And then the exponent is going to tell us how many times to move that decimal. Now let's say I'm still stuck in moving it left is positive. So I see positive, so I move it left. I'm not saying this is right. Let's see. So I'm going to move it left 4 times. 1, 2, 3, 4 times. I'm going to need some filler zeros. There's my decimal, which says that this is 0.000512. But is this right? Like I said, I might be doing this wrong. I may have pulled out the red marker for a reason here. Let's use that highlighted self-check. Small numbers are supposed to have negative exponents. Big numbers are supposed to have positive exponents when in scientific notation. That 4 was positive, but this number 0.000512 is small, which says we did it wrong. So what do? We start from scratch, and instead of going left, we go right. If you do that self-check every single time, if you ever do it wrong, if you ever move it in the wrong order, you will correct that mistake. I cannot tell you how many times that has saved my butt. Now, if you move 17 times instead of 4 or 5 times instead of 4, it's not going to catch that. So I need to erase all of this. Okay, now let's pull out our blue marker for correct. Okay, so we still write our 5.12. The exponent is a 4, so that tells us to move it 4 times. But now we left seem wrong, so let's move it right. 1, 2, 3, 4 times. Got some fillers, so put some zeros in. So that says this should be 51200, which is 51,200. But is this right? Well, this was a positive exponent, and this is a big number. So yes, it's correct. It's supposed to be 51,200. You can go back to the previous problems and use this little self-check. 38,000 was a big number. It led to a positive exponent. 0.053 was a small number, negative exponent. 0.000007, small number, negative exponent. This 328 millions, billions, trillions, whatever that is, that's a big, gigantic number, positive exponent. 0.7 is a small number, negative exponent. It works. Even I left one of them that I did incorrectly, or it was like a previous self-check. Here's the 7.05 with a positive 1. So that says it should be a big number, which would have been 70.5, but the original number was 0.7, so that's why it was wrong. There are lots of ways to check this. So before I even start going to move it, now let's use this highlight memo to tell us the direction. So for number 7, this exponent is negative, so what kind of number should we be making, a big or a small? We're supposed to make a small number. So if I wrote this 6 and I start moving it right, that would be 60, 600, 6,000. If I kept going to 6 million, 6 billion, 6 trillion, this would make a big number and would be wrong. So we don't move it right. Again, if you're thinking about this as you go, you can correct yourself. So instead we write the 6 with its decimal. Remember, right will make the number bigger. Moving it left makes it smaller. 1, 2, 3 times. Filler zeros. And we get 0.006. That's a small number with a negative exponent, so it works. Otherwise, we would have ended up with, what was it, 6,000? That's a big number, which does not lead to a negative exponent or come from a negative exponent. Alrighty. The state of Rhode Island is approximately 1.212 times 10 to the third square miles. So Rhode Island is the smallest state. So that is the smallest area, because square miles is an area, of all the different states we have. The rest of them would all be larger than that. Not that that matters for the problem. They just want us to write this in standard notation. So we write our 1.212. Now let's see, this 3, that was a positive exponent right here. So that means we should be making a big number. If I move this decimal left, that's 0.1, 0.01, 0.001, and those are making small numbers. So that is not the direction we're supposed to move it. If we move it right, 12, 121, 1,000, etc., that would be making bigger numbers. And that's right, 1, 2, 3 times. So this becomes 1212 mi squared, or you can use the word square miles. That's a big number. And it came from a positive exponent, so it checks out. Again, if I moved it 4 times or 2 times, that's that big number positive exponent, small number negative exponent ain't gonna work. Big, positive, small, negative. Big, positive, small, negative. You could also relate that to a number line. Bigger numbers are positive, smaller numbers are negative. But we're not actually talking about the sign of the number, we're talking about the sign of the exponents. It's just relatable in that manner. The last, final, new example we will do for the course. So we'll still talk together next week. Well, you know what I mean, the next couple classes. But we'll just be doing some review stuff. I would love for you to email me some questions or get in the live lecture like no one's doing. All my other classes, most of my students are coming to live lectures, but from a math threes, not really anyone's been able to show up, and that's understandable. So I would love, at least if you can't come to the live lecture, and I know from one of them, because of complications, I haven't been doing the live lecture most of the time. I've just been pre-recording it. And I'm sorry I have to do that, but there's no way around it. Anyways, what was the point I was making? Please email me questions if you can't be here live. That way I can go over them for you, whether it's a direct connect homework question, a quiz question that you worked on and can't quite figure out. And I know some of you have been emailing me questions, but I'd love to hear from more of you. I really would. Some of you are doing an okay job keeping up with the pace, but I really do wish that a lot more of our class was able to do so. All right, rant aside. Number 9. A butterfly sanctuary has butterflies that weigh between 4 times 10 to the negative 2 grams and 3 times 10 to the negative 1 grams. So they just want us to write both of these numbers in scientific notation. Now these numbers both have negative exponents. So we should be creating small numbers for both of them. But this is 2 different problems. So for the 4 times 10 to the negative 2, here's the 4. We need a decimal after the 4 since it doesn't have one initially. The exponent's a 2, so that tells us to move it twice. Now, I'm going to do it maybe right, maybe wrong first. Let's see. If I go right, 1, 2 times. That would be 400, which is a big number. Nope, negative exponent, supposed to be small. So we go the other way. 1, 2. Ends up there. There's a filler 0 we need. So that is going to become 0.04. And they had grams, so let's use our units. So a butterfly sanctuary has butterflies that weigh between 0.04 grams and 3 times 10 to the negative 1 grams. So for this one, again, negative exponent, so we should be creating a small number. Let's just write the 3 and a decimal after it. The exponent's a 1, so we know we need to move it once. And I mean, we just did it, so hopefully you don't go wrong, but maybe you try and move it right once. That'd be 30, which is a big number, so that's wrong. So we move it left once, which gives us 0.3 grams. Remember, if you just write 0.3, it's still correct. And that's it. So our butterflies weigh between 0.04 grams, which is a very small amount of weight, and 0.3 grams, which is also a very small amount of weight, but almost 10 times as much as the other. This is like saying you've got dogs that range from 4 pounds to 30 pounds, basically. So the final memo I want to make is, I mentioned this in passing earlier, but I want to make sure I write it down. The scientific notation, let's just show this one example, 4 times 10 to the negative 2. There is a secondary way to write this. You can do 4 dot 10 to the negative 2. It doesn't matter if there's a dot or an X between them. Some programs prefer the dot, some prefer the X, some don't care. Handwritten, I don't care. If for some reason on a test, if Connect Math does care, because we have to use so many programs, I can't keep track of them. If on a test you wrote the dot and it marked it wrong and everything else about it was right, I'd give you full credit for that. Or vice versa, if you wrote the X and they mark it wrong, I'd go back and give you full credit for that. I hope that since the textbook is using the X, that the X is what they're accepting. But again, I can't promise. Connect can be weird. So that's it. We have now covered every single solitary bit of information that will be on the final exam. So I'd love to just kind of say a couple of memos, and then we'll call it a day. I don't have any review material prepared, so we'll start working on that next week, Tuesday, Wednesday. So for my Tuesday, Thursday classes, Our last class is Thursday, May 7th. So that means final exams are due by 11:59 p.m. May 7th. If you have not passed your final by that point, you will not pass this class. Remember, it doesn't matter what you do on any particular homework, quiz, or test. The point of this course is you have to get to the final, you have to take it, and you have to pass it. For my Math 3 on Monday, Wednesday, our last class is Monday, May, what is that, the 11th? Yes, I thought so. So final exams are due by 11:59 p.m. PMMM, May 11th. To take the final, you must pass, remember that's an 80 or higher, all homeworks and quizzes, and you must pass with a 75 or higher, all tests. Now remember that was test 1 and 2, test 1, test 2, A and B, then test 3. There is a review for the final, I believe. So please make sure you do that. And to pass the class, you must pass, which means a 70%, the final exam. Not passing the final means you fail the course. You'll either get an R or a U, depending on how far you make it in the course. Quite honestly, the difference of the R and the U is negligible. It's only for bookkeeping for the administration, as far as I've been led to believe. Remember, there is no GPA associated with this course. There's no A, B, C, D, or F. We are not using the new TCC grading scale because this is a developmental course that's not tied to GPA. The new grading scale, which is optional for credit level students, most students, there are exceptions. Those are okay. You don't really feel like you want an A, B, or C. You just want to have your passing grade because maybe you got a C, and all this teaching at home kind of thing affected you, so you don't want that C on your GPA. Well, again, this class doesn't have a GPA, so we are not changing grading scales. You can still fail this class by not passing the final exam. Which again, I am scared for how many of you are even going to get to take the final exam because of your progress throughout this course. I've sent emails asking for responses. I didn't even hear from most of you. I still would love to hear from you. I'm going to send out more emails about that. Remember also that you only get 2 attempts on the final exam. This is not my policy. This is TCC's policy, as well as I believe the state's policy. So if you fail the final exam once, make sure that you pass it on your second attempt. Make sure that you study between your first and second attempt. So what I'm saying is it's a bad idea to be taking test 2 and test 3 the day before your last day of class, or even on the last day of class, because that's going to rush you and you're not going to have time to finish everything. So you need to start really hammering away at this material if you are behind, if you're a section behind, if you're a chapter behind. This is it. This is the time to start shining. You are allowed a calculator for the final exam. So even if we were doing this class regularly, this would be the standard policy. We opened up the chapter 3 test to being calculator for the whole thing. That changed. This part is not changing. What did I want to say? I think that's going to be it. So we're going to call it a day there. Like I said, next class, we're going to come in. We're just going to kind of lightly review stuff. We'll go over some other examples. And yeah, and we'll get a couple classes of that, I think. So have a good one. Get your homework done, get your quizzes done, get your tests done. Email me if you need more attempts, whatever it is. Email me if you have questions. Please, please, please communicate for me. I need to hear from most of you. All right, have a good one.